We're going to move on right now and talk a little about sea level changes, which is very important for Central Texas. One really cool thing you can look at in cross sections of rock is by analyzing the particle size, the grain size in the rocks. You can determine whether seas were rising or falling during particular deposition sequences. So you can really read sea level change kind of like a book if you're looking at rocks in the right way. So for this, what I want you to do is reference that transgression regression handout that I gave you earlier. So let's first focus on the transgression side. What I want you to notice about this first is the key. So these are 3 rock types that I want you to be able to know. And I want you to know not only the types, but I want you to know the symbols and the grain size. And this is not much, it's only 3. So the first is sandstone, symbolized there. Sandstone is symbolized by dots. The second is shale, which is symbolized by sort of dotted lines in there. And the third is limestone, which is symbolized by sort of a brick appearance. I then want you to pay attention to what's down there, which is particle size. Sandstone, of the 3 rocks here, has the largest particle size. If you've ever experienced sandstone before, and you should if you have not, if you ever experienced it before, break it up, you can actually isolate the individual grains. They're like grains of sand. Such is not the case really as well for shales, which are clays. If you break up a clay, the particle size is much smaller. And if you've ever experienced limestone, writing on the street, chalk rock limestone, those particle sizes are extremely small. So we're going from sandstone being the largest particle size, shale medium-grained rock, to limestone being very small-grained rock. What this diagram is showing are 3 deposition events. One's kind of at a really old time, one's at a sort of a medial time, and one's a very young deposition episode. And what's happening between these 3 episodes, and you might be able to notice already, is that the sea level is rising. You can see the sea level rising in that landscape. What we have here is really a diagram showing runoff. So if this is water flowing off of a continental margin from rivers or streams or whatever into an ocean or a larger body of water, you can see characteristic sedimentary rock sorting. Notice what gets deposited furthest out. It's limestone, which has the smallest particle size, and that makes sense. It's the smallest, it's the lightest, it's going to travel the furthest in the larger body of water and get deposited the furthest from the shoreline. Closer in we have shale, closest in we have sandstone. Look what happens when the sea level rises. So again, that was deposition event number 1. Let's say between deposition event number 1 and deposition event number 2, the sea level rises. We're now right here, our sea level has risen. We have the same pattern. Limestone deposited furthest out, shale deposited in the middle, sandstone deposited closer in. But notice our limestone sort of frame of reference has been shifted over a little bit because our sea level has risen. So whereas limestone was being deposited out here in the first example, since the sea level has risen, we're now getting limestone deposited closer in on top of what was before shale. This will make sense a little bit more later. Let's look at the youngest deposition event. So now our sea level has risen again. We have limestone being deposited out here. We have shale being deposited closer in. We have sandstone being deposited even closer in. So why this is important is, let's say seas fall at some point in the terminal Cretaceous, okay, and let's say 2 weeks ago people are cutting down to form a highway in Austin, and this cross-section is exposed. What do you notice about this cross-section? Well, I'll zoom it in over here and kind of draw the 3 layers associated with it. What you should notice is that sandstone is on the bottom. In the middle, we have shale, SH, and on the top, we have limestone. Now, why is that significant? What this is, as we go up through the rock record, you might notice that the particle size is fining. And I just erased that with my or drew over it with my pen. So let me erase that. Fining rock sequence, meaning the particle grain size is getting smaller. This is because our frame of reference has been shifted over from here to here to here. So we have limestone at this point being deposited on top of what was in our first deposition event down here, sandstone. So we have limestone on top of sandstone. What that looks like when you're looking at a cross-section is you have the largest particle size on the bottom, medium grains in the middle, and the finest particle size on the top. Again, that's called a fining upward sequence. What this means, if you see this in cross-section, if you see the grain size of rock layers fining as you go upward in the rock record, that means that the seas were rising during that deposition event. That's called a transgression. So if a marine transgression was taking place during a deposition event, you can notice that in the rock record by the fact that those particle grains are fining as you go up, getting smaller and smaller. Sandstone, shale, limestone, smaller and smaller. This opposite diagram is depicting the opposite process. So again, we have runoff from streams, rivers, etc. hitting an ocean. Notice we have the same process happening. Sorting, limestone deposited furthest out, shale deposited in the middle, sandstone deposited closer in. Except from time 1 to time 2, sea level is falling. So here, sea level's there, and then at time 3, sea level's there. It's falling. So let's take a look at the strata if we randomly got a cross-section right there. You would see that, I can zoom that out over here, on the bottom you'd have limestone, in the middle you'd have shale, and on the top you'd have sandstone. So limestone, shale, sandstone. This is the opposite of our previous diagram. This is called a coarsening upward sequence, and that is exemplified when sea levels fall over geologic time. It's called a marine regression. What that means is, if you're looking at a cross-section and you see smallest grain size on bottom, above it medium grain size, above it large grain size, you're getting, as you go up in the rock record, a coarsening upward sequence. What that means is that the sea level was falling during that deposition event. So we have two conflicting processes here. If you have a fining upward sequence, rocks going from on the bottom, larger grains, then on top of that medium grains, then on top of that small grains, that's a fining upward sequence. That indicates that during that deposition event the seas were rising. If you have small particles on bottom, medium grains in middle, large grains on top, that means during that deposition event, seas were falling. So we can really read the geologic record to determine what sea levels were doing throughout geologic time millions of years ago. Pretty cool concept.